Take a little bit of time here to get this structured, set up. But as we do that, please join me in welcoming warmly to the City Code stage for the first time, Michelle Brush.
I'm not going to be seated. All right, thank you very much. This is going to be a bit of a journey because it is really, the whole talk is just things I really like, which is a great opportunity to be able to get up and just talk about the things you really like that you've gotten to use, that you've had good use out of it. And since it's going to be a journey through several algorithms and data structures, I think it'd be good to start with knowing where we are. Where are we right now? This is our latitude and longitude, and in case you get lost and need to find something later, you can always refer back to this. I also think it's good to talk about algorithms and data structures in the context of a problem. It's not very interesting to me just to hear about, here's how it's structured. I want to know how it can be used. So we're going to create a problem for ourselves. We know where we are. We're going to assume that we have a data store of all of the bars in the world, every single possible bar we could go to. And we're going to ask ourselves, where can we find a nearby place to have a beer? Because I love beer, all sorts of beer. Already have tried many Chicago beers while I'm here. This is actually an interview question that I used to ask individuals when I was interviewing. Just to get a conversation started about problem solving and how they approached problems, I'd say, hey, write me an API to support searching for the nearest bars or restaurants or anything like that. And I asked them to start talking about how they do it. And I always hope somebody would just walk in and say, well, I'm not going to write it. I'm going to call something else that already exists. Google already did it for me. No one ever said that, ever, in all the interviewing. And I think that's what a mature engineer would say, is like, why would I write that? And that's because I believe pretty strongly sometimes our jobs are to find ways not to write code. Like, let's just not do it. Let's find another way to go about it. But if somebody had said that, I could have just rephrased the question, because it's not like if they'd said that, I'd be, you're hired, let's go. I'd want to see how they actually solve problems other than just reading documentation off the internet. And so I would have had to rephrase it, okay, we're going to do this from scratch. You're really going to do this on the whiteboard or on your laptop with me. And I ask this question a lot because I interviewed a lot at both companies that I've worked for so far. I've worked for navigation companies, I worked for healthcare software companies, and I've interviewed a lot because that's kind of one of the things you end up doing when you grow in your career. And so of all the people that I've interviewed and asked this question, I would say about 25% actually gave me a good answer, a really good answer. And that was okay, because I don't really feel like interviewing is about finding the right answer. I feel it's really just talking through how people think, how they take feedback. But it was interesting to me that only 25% could actually give me an answer that worked. Most people gave me this, which is fine. I love binary search. We all learn it in our computer science degrees, and we use it all the time, or call something else that implements it for us. But it's not exactly the right solution. It's also something that I think like even a layman knows. Like, they don't know what it's called. Nobody, your grandpa, your grandma, your aunt, they don't know what binary search is, but they know how to search a phone book, or at least they used to. Not so much anymore. Now phone books just end up in the recycling as soon as they show up. They're also really inefficient at binary search because their pivot points are really bad. But one of the things that's inherent in binary search is that you have to have a sort. You have to know how to actually order the data such that you can do that whole traversal of looking on either side of the pivot point and figuring where to go next. So whenever somebody would just kind of say binary search in the interview process, I'd say, great, tell me your sorting algorithm, because it's not very interesting unless you can tell me how to sort the data. And naively, they would almost always say, well, I'll just sort by X and then by Y. A lot of Java programmers have written their comparators. They know how to do that if-else. They'll just do that on the two variables. Well, that breaks pretty easily. And as an example of why that breaks, United Lily Growers in Smith River, California is exactly the same latitude as where we are right now. But the Green Door Tavern is a little south. So it would actually find United Lily Grovers, which is actually a horrible bar because it's just about lilies, before it would find something that's actually only 1.26 miles from us. So sorting by X and Y just doesn't work. And this is because in that kind of approach, you're giving preferential treatment to one variable over another, and it doesn't really deserve it. When we're talking about spatial reasoning, X and Y are equally important. You're not trying to just find one in only one space. The comparators that we usually write make sense when we are favoring something, like if we care about cost more than we care about number of features or something along those lines. So at this point in the interview process, I'd usually get an answer that's basically brute force. They wouldn't say, well, I'm just going to do brute force, but they would propose to me a brute force algorithm, which would be iterate over every single bar in the whole world, calculate the distance, sort by the distance, and then pick the best one. And that works. You know, brute force works. It's not very interesting. It's not fun to write. Not very efficient, but it works. And there's 630 bars in Chicago alone, so Chicago's maybe in the top 50 largest cities, depending on whether you're counting the suburban areas as well. So it's not going to be very efficient, you know, especially when we start thinking about rural bars and all sorts of interesting places on, you know, I-70 or I-35. It's not going to be that great of an answer. So we need a better answer than that. So some of you might be wondering right now, is there a right answer? Well, of course there is. That's the basis of my talk. You also might be wondering if I'm just a really mean interviewer. Like you're thinking right now, you never want me to interview you. And that's probably true. I am a mean interviewer. I think that the whole point of interviewing is to see how people would react to feedback. And so I intentionally sometimes pose hard questions, not because I expect them to get the right answer, but I want to see how they react to being told they're wrong, because I feel like our careers in programming have this long trajectory of people openly and publicly telling us we're wrong all the time through code reviews, design reviews, whatever it happens to be, pull requests. But like I said earlier, some people got it right, and that was really interesting to me. Now, I didn't automatically hire everyone who got it right, because if they took feedback poorly, then that was still a problem, whether or not they were smart. But I did notice a pattern in the people that got it right. You know, I'm pretty open about who I interview. I don't require a computer science degree. If you know how to program and you can reason, then that's, you know, something I think should give you an opportunity. And so some of the people that I interviewed were physics majors. They had picked up programming in their spare time. They found it really interesting. And I found a strong correlation between people who got it right and that major. If they're physics majors, they usually did quite well. And that was because they take an interesting approach. Their background in trying to reason about particle collisions, or you can even say like big object collisions in space, made them have to have spatial reasoning and understand how to deal with things that are in 2 dimensions or 3 dimensions. And they would do a very simple approach, which is they'd say, let's take the space of all these particles, and let's cut it into 4 parts, and then let's take each of those 4 parts and cut them into 4 parts, and just keep cutting the space until you got to something really small that you could reason about. And by small, it could be small in size, it could be small in distance, or it could be small in terms of the number of items in that space. You could actually do it based on capacity. You could say, I want a single square to only have 10 items in it, or 3 items in it. Then you describe each of these squares or rectangles based on either the center point, which is if you want to save space, you would just say the center point of it, or you can describe it based on the 2 corners, and that's called creating a bounding box. And either way, it's really easy to reason about, because you just have to understand, is what I'm looking for close to this center point, or is it within this box? Basic less than kind of operations. And then you create a tree of all of those nested squares or rectangles. And if you want to find something, you just have to follow the rectangles all the way down. So is it in this box? Is it in this box? Is it in this box? Until eventually you find it. This algorithm is called a quad tree, or data structure / algorithm. John Bentley and Raphael Finkel came up with it in 1974. I kind of struggle between whether I want to call it invented it or discovered it, because part of me feels like data structures are more discovered than invented. But in any case, they were the first people to describe it. And you may be familiar with John Bentley, because he is the author of the Programming Pearls series of tips for programmers, which I love. He also gets a lot of, I want to say, infamy for the fact that he wrote a buggy implementation of binary search in programming Perls, and Josh Block later called him out for it. Now, he did teach Josh Block, so Josh Block owes him a lot, and, you know, it's good. And I would get quadtree every now and then as the answer, and quadtree is a really good answer. And not only because it actually solves the problem and doesn't cheat and is efficient and is not brute force, but also because it can be generalized to more dimensions. You don't have to just cut 2 dimensions into 4 pieces. You can cut cubes into more cubes, and then you have an octree. And at this point, you could even go more, but then it gets hard to visualize on a slide because we just struggle with visualizing higher dimensions than this. The nice thing about this approach is it also applies to more than just spatial searching or trying to find things in some multidimensional search. It also applies to compression. That's one cool thing I really like about quadtrees. Because if you have an image and you want to compress it, and parts of that image are very uniform in color, then you can actually leverage this breaking of the image into 4 pieces to try to color a single square or rectangle and only store it once. And to show you what that looks like on my llama, we would cut it, and we'd keep cutting it, and we'd keep cutting it until we got these uniform squares. And in the minute we got a uniform square, we'd say, OK, done, we're not going to cut this anymore. We're just going to represent this one square rectangle by a single color pixel. And you just keep going and going and going, and then I got lazy and stopped drawing. But eventually you would cover the entire thing and get down to where you'd have a lot of pixels represented in a single rectangle that was very big. So getting back to the spatial search problem, though, we still want to find a bar. I talked about binary search as not being necessarily a bad answer. The problem is more the sort and what people did with it. And the challenge specifically with the sort is that you really, in this case, you have 2 values and you need 1. And where we traditionally get kind of lazy in our programming and just write that quick comparison function that is leveraged, we just basically do an if-else, and we say if the first variable is equal, then we look at the second one. And that can be almost explained as if we're concatenating the 2 bits, or it's concatenating the bits of the 2 numbers. So basically, if I was doing that with my x and y values, I was basically taking all the bits of x and then appending to the end all the bits of y, and that's why x gets so much priority, is because it's the higher part of the number. And that's why it doesn't really work very well when you want those 2 things to be equal. So can we cheat? Can we still manipulate the bits and get a number that actually behaves more closely to we want it to in terms of that sort? And the answer is yes. We can interleave the bits. So this is a little harder, but basically we just take the first bit from the first number, the first bit from the second number, and we just interleave them one by one, just weave them together. And when I first heard about this, I thought, that can't possibly work. That seems very, very simple, like almost too simple. And I think all great algorithms and data structures, when you hear about them later and you have that sense, that means they're really great. Like, they're really great if you think, oh, that's too simple. I could have come up with that. No, you couldn't. But the person who did come up with this was G.M. Morton, and he did it in 1966, and he called it Z-order. And the reason why he called it Z-order is because when you do that, interesting, you make a bunch of little z's all over the place. And so kind of watch that. I'm just going to have this really simple coordinate system where you have zeros and 0 through 3, 0 through 3. And we take the bit representation, and we say, OK, well, this newly created number we have represents the order. So 0 comes first, 1 comes second. We've taken the bits from each coordinate. And we see we can start here, and when we're all done, we're going to end here. And let's watch how that works. So we're going to start here, and we're just going to kind of move through the space. And this is the order. If we were sorting them, they would be sorted in as I move through. So that made a little z as you watched it. And there was like kind of nested z's in there, and so kind of watch how that would build out. You could have this z structure. I kind of inverted the coordinate system a little bit for this picture because it's easier to follow that way. And I could build a bigger set of z's and connect them, and their connections still make a z. And I could do that again and make something even bigger. And then I could do that again and connect them again and make just another z's of these blocks of z's. And as I do that, you may have noticed that it feels more and more like it's getting more dense. It's getting more solid. It's almost like it's going from this one-dimensional line and creating this two-dimensional shape. And that is what it's doing. What's really interesting to me is that z-order is actually a space-filling curve. And that means if it's a space-filling curve, it's actually a fractal. Because the definition of a fractal is anything that appears to act as if it has more dimensions than it really has. And since a line has one dimension and this shape starts to appear as two dimensions, well then it's now a fractal. And that's just really cool to me. I always wanted to use fractals my entire life. And then I started to work in navigation systems and had to actually search for things in space. And I was like, oh, I get to use them finally. That's because I'm a math geek. I got into computers that way. And what's really cool about bit interleaving is, again, it can be extended to multiple dimensions. We can do this in 3 dimensions. We can do it in 4 dimensions. We can keep doing it on, because it's this really simple operation of just picking a bit. Now, you'll have to have very, very large numbers in terms of 128-bit and keep going on up. But it works. It's really interesting. But I don't want to just talk about spatial search, because that's not the only problem we ever face. I'm going to kind of transition a little bit and talk about graphs, because graphs are actually the thing I really love. It's what I really fell in love with in my career. And it started before I ever got my first job working with graphs, and started when I was traveling with my sister to visit my dad, and he just moved to a new subdivision. And we got lost. And we got lost because the geniuses that built the subdivision felt that every single name should have a tree theme and that they should reuse words. So blue spruce and blue fir and lane and court was just peppered all over the place. And I could not for the life of me remember what streets we were supposed to turn on. And I didn't have a navigation device. I didn't have a cell phone. And I needed to be able to find my dad's house. But the cool thing is I did know that the housing structure kind of formed this little tree. I knew there were no cycles. And I knew that I could find anything because there was really only a branching factor of 2 throughout the subdivision. You might wonder, how did you know that? Well, I looked at a map before, then I forgot where I needed to go. And so my sister was the one driving, and she said, oh my gosh, we need to drive back to the store and use a payphone, because those still existed when this story happened. And we need to call Dad and get directions. And I said, no, we're just going to go right. She said, what? I said, we will always go right. No matter what happens, we face an intersection, we're going to go right. And she thought I was crazy, because she's imagining, like, her view of the world is like, I'm telling her to go just in circles around a block. And I said, Katie, you got to trust me. Just go right. Well, I wasn't the first person to come up with that, obviously. Go right is a strategy for solving mazes. You may have heard of it more formally as depth-first search when you're working through a graph. This was actually determined in the 19th century, which is really interesting to me, and that's because there was a lot of hobbyists working with mazes, and so they came up with this algorithm to figure out how to solve a maze that we later now use to search graphs in computer science, so that's kind of cool to me. The reason why they came up with depth-first search first, and probably not the other search algorithms that we're going to talk about, is because I think it's the one that translates the best to an actual efficient travel model. If we talk about other search models, we may require teleportation to actually execute on them, and we don't have that yet. So one of the other algorithms I'll talk about real quick, just to kind of lead the way to the one I really, really love, is this one, which is basically if you have a graph, and for simplicity I made it look like a grid, and you have where you're starting and where you want to go, you can actually find where you want just by kind of walking through what we call all of the adjacencies, or all of the nearby nodes in the graph. And you basically evaluate each node in the graph and just look at all of its nearby neighbors and keep going through until you finally find what you want. And I feel like this process kind of makes like a little cycle, like we're just kind of circling out, ever expanding. Maybe it's more like a spiral as we work through the graph and find what we're looking for, and then we eventually find it. And that approach is breadth-first search. And that's the one that would require teleportation, because I'd have to be jumping between all the intersections. It was discovered in the 1950s, so it's not interesting to me, because that's not the time period I want to talk about. It's also not interesting to me because it doesn't really map to what we feel a lot in the real world, which is most graphs we're trying to work through are weighted graphs. When we're driving, this is because there's speed limits we have to honor, or there's traffic. So we really want something that understands that I want to find the most efficient path. I just don't want to find something. Me going right through my dad's subdivision was a horribly inefficient path, but I was able to find the house. So here's my example graph for if we had a weighted graph and how would we want to solve it. And an algorithm that we could do could be, we could say we wanted something called an open list. And the open list would be all the things that we have in our memory that we'd like to consider. And then we could have and we could order that open list based on the cost to get there. So we could say we're going to keep this thing sorted, and we're going to keep track of what energy, gas, time, whatever it was that we had to spend to get to this point. And then we could have another data structure, which is a closed list. And the point of this is just to say we've already visited or closed a node. We've already seen it. And that's to keep us from going in cycles in cases where the graph does have cycles. And very simply, we could actually start at our destination and put that on the open list and say the cost to get there was 0 because we started there. And then we could look at all of its adjacencies or all of its neighbor nodes, and we could put them on the open list, their cost to get there, which at this point would just be their weight. And then we could go through each node that way, and as we were done with each node, we move it over to the closed list and we look at its children, and we just work through until eventually we're going to find what we're looking for. So this algorithm should all be very familiar to people. May not have seen it described this way, but if you've done anything with graph search, you probably have done Dijkstra's algorithm. And I feel like this is the one that I guarantee people know. Not only that, but I used to ask when I would talk to new engineers, tell me like one famous computer scientist or one famous computer programmer that you know about. And at the time when I first started asking this question, it was really hard to get any answer but Dijkstra. And the reason they knew Dijkstra is because they learned Dijkstra's algorithm and it had his name in it, and so they could remember that. Getting them to other people, anyone out in the industry currently was always a bit of a struggle. But I'm not going to talk about Dijkstra's anymore because, again, that's from the 50s, and I said I'd stick to the 60s and 70s. I only really brought it up because it's really easy to understand what I'm about to talk about if you know Dijkstra's. And what I'm about to talk about is A-star. A-star got me a job once. I was interviewing for a navigation company, and they asked me if I'd ever done anything around any sort of graph search. And I said, yeah, in college we did some stuff with robotics, and we were trying to find, some things through an obstacle course, and we had to come up with an algorithm. I said, but it was nothing fancy at all. And the interviewer asked me, he said, well, what did you use? And I said, oh, just A-star, nothing special. And the navigation company was like, oh, we use A-star. So then I came off as like this overqualified person because I felt like A-star was like a piece of cake, and they hired me. But A-star works a little differently from Dijkstra's in that we still need an open list, we still need a closed list, but we also need some information about what it's going to take to get to the goal. And that may be distance. A lot of times it's line of sight distance if you're actually dealing with real coordinate systems. But it may be just any kind of insider information we might have about what we think will get us there. And so on your open list, instead of storing just the cost to get where you need to go, you also add to it that heuristic value, whether it is that line of sight distance or something else you come up with. There's a whole bunch of variations that I'm not going to get into now, but if you find me later, I'd be more than happy to walk through some of them with you. And that's how you work through the open list. You use that cheating, that insider information. And so what that would look like with the same graph is we'd kind of start the same way, except things do start out with a cost because they had that cost of the distance to get there from line of sight. And we'd work through it, and eventually we would find the same node we were looking for, but we'd find it faster. We didn't have to look as many nodes in the graph because we used that heuristic information to cheat. And so when I worked with graphs, I like to think of it this way. I like to visualize things with pictures a lot. And so I would think of breadth first search as being this circle. It's going to look at everything, ever increasing, spiraling out until it finds the thing you're looking for. And then you look at Dijkstra's, and Dijkstra's actually accounts for the fact that things have cost, so that things can be expensive. And so it's not going to look at everything because some things are going to be prohibitively expensive to even consider as an option. And so it's going to make this like weird kind of fluffy cloud in terms smaller than the breadth first search, but still covering quite a bit of that area. A-star is my favorite because with that insider information, you can actually pull towards the destination. So you don't consider as much around your source because things that are behind your source or near your source tend to have a very expensive heuristic value, and so you discard them very quickly. I used to think that it often makes egg shapes when we would look at the graph coverage and how we were searching it, like A-star's an egg, Dijkstra's a cloud, and breadth first search is a circle. And this is the power of heuristics. Now, the funny thing is, if you actually go out and look in the industry, people who are really practicing algorithms related to pathfinding or graph search, you'll find that all three are still used. They're just used based on different constraints. So if you have a situation where all of your edge weights are equal and you don't really have this concept of cost, you don't have a weighted graph, then you might as well just use breadth first search. There's not much value in trying to build with something more complicated. If you know that you have edge weights and you want to find the most efficient path, but you don't have any sort of insights or heuristics that you could build around where you're trying to go, well then Dijkstra's is kind of the obvious choice. However, even in the case where you do have insights about your target, you have to look at what's more costly for you. Is looking at a node and figuring out all of its adjacencies or neighbors and evaluating them costly, or is calculating your heuristic very costly? So an example of this, what I've run into is, working with embedded systems, depending on the hardware characteristics, the graph may have to be stored on disk, and disk operations may be very expensive. And if the graph is stored on disk and disk operations are very expensive, then you want to not close or look at as many nodes because that's your most expensive operation. So you're going to want a heuristic because you're going to try to minimize that I/O. But on the other hand, if you've really spent a lot of money on your hard disk and you went cheap on your CPU, well, then in that kind of world, calculating the heuristic is really expensive. And so you're going to want to do Dijkstra's because then you don't have to do those calculations, but going to disk is really cheap. Or if you can store the whole graph in memory, which is pretty rare. And so all of these algorithms are still relevant. A-star is just my favorite. And the reason why is, again, it gets back to I'm a math geek. And when I fully understand all these algorithms, I realized that A-star was the most general form of all the other ones. Because they all kind of behave the same, and you can generalize them all to needing an open list, needing a closed list of things you've already visited to prevent cycles. But what's different is how you cost and how you sort that open list. And in breadth first search, we're just treating everything as constant. We don't care. Everything's the same value. So it's basically first in, first out kind of approach. In Dijkstra's, we say the cost of the weight to get there, the whole cost of that path. And so that's our g of x. I still threw the constant on there because it makes it constant can be 0. And then A-star takes that heuristic plus the cost plus that constant to get there. So, and this is also interesting to me is that A-star was the last one we discovered. It was the generalization, but it was the one that was discovered the latest. And that's kind of funny how things work that way in our field. I want to talk about how we can do more than search with graphs, though. Graphs aren't just there for searching, for finding a path or understanding how to traverse through a set of nodes. Graphs are actually interesting for other reasons, and that's because we can do pattern matching with them. Or more specifically, we can build up a rules engine. So in 1974, Charles Forgy first produced the working paper on the Reedy algorithm. He didn't really publish a full, peer-reviewed, formal paper until much later, but I'm going to cheat and just go ahead and use that 1974 date because I want to talk about it. And he came up with a way to leverage graphs in order to represent knowledge patterns so that you can more efficiently evaluate rules in expert systems. And when we look at how rules typically look in expert systems, you usually have a series of premises, and there can be 1, there can be 5, there can be 200, who knows? And those premises typically yield a conclusion. Sometimes in expert systems, we're trying to get it to not just yield a conclusion, but we also want it to yield that the system should take some sort of action. If we're doing advertising, maybe it's send out a spam email, or in my case, if we're doing healthcare, it might recommend some sort of clinical intervention. And rules could be represented in either that kind of addition, subtraction looking kind of way that I show, but it can also be represented in the more traditional way, which is that you have this left-hand side that contains all of your premises, and then you have this right-hand side that contains your action or consequences. And I strongly believe that most engineers are lazy, and that's a good thing because lazy breeds efficiency. And so we tend to abbreviate things. We might call one side the LHS and the other side the RHS. It's just a way to simplify things. And this is how we understand rules. And we can have a long list of these in a system. So where I work is in medical software, and medical software has a lot of knowledge. The medical field is just a tremendous amount of knowledge. That's why they built Watson, right? And And we have to capture all that. So we have tons and tons and tons of rules that represent these really complicated things. And so representing them this way can be very expensive, especially if you realize later that when you want to actually go match on one of those rules to determine the consequence or to fire off that action, that's a lot of pattern matching down the way. So what Charles Forgy recognized is that really rules are a directed acyclic graph. That's all they are. The path is basically the series of premises that you have to do to get to the conclusion, and the conclusion is just a leaf node. It's just a point in that graph where you stop moving forward. If you're familiar with a trie, or some people say tree, I say trie because it's just easier to reason about when we're talking out loud, which is a structure that's very specialized tree that actually allows you to do pattern matching by mapping strings onto nodes and then not duplicating any of the path to get to a node. So in this case, I have Chicago, and I also have chicken because they share the same path, and they just diverge at the place where they're different. If you're familiar with these, then this is going to be very easy for you, because the Reedy algorithm is really just like a trie, but mapped onto rules and knowledge as opposed to a string. Basically, for the algorithm, you start out with a root node, because you have to start somewhere, and there's one root node. And then from that root node, you have a series of type nodes. And the type nodes represent basically the types of objects you want to deal with. If you're thinking of like an object-oriented programming language, these would be your objects themselves, the classes. But it might be something else in other languages. But it's just your way of saying, this is the type of information I'm dealing with. And the idea is that you don't exercise your rules unless you have a type that matches something that you care about. Once you've identified the facts that you have, and that's what enters at the root, is the facts, that match the types, then you can move on to your selection nodes in the graph. And the selection nodes have the criteria that determine whether something should really be true or not. So it's your less thans, your greater thans, your equals, anything that's that Boolean, that's what that selection node is. It determines whether or not your type actually matches what you care about. And then optionally, you can have negation nodes. So you can say something is not that, and you would put them in. And then you can have join nodes. And join nodes are where you're bringing two objects that have met that selection criteria together in order to say that these things both have to be true. What was interesting to me when I learned Reedy is that they only really support and in the most basic form of it. So you've got not and you've got and, which means you've got NAND, which means then you can build anything if you've done a lot of logic programming. But it does mean that there's some weird consequences to not being able to have this like first-class OR. Now, different rules engines will go ahead and create an OR that hides that from you, but that was interesting to me to know that. So you can join based on an and. And then finally, you get to your terminal nodes, which represent the actions or conclusions. So if you're able to follow a path all the way through and your fact still applies, well, then you execute whatever that terminal node is it tells you to do. Now, the real power of Reedy was not just this structure. It was also understanding that it's more efficient to store some of the knowledge that you've gained throughout the processing in memory. And so throughout the graph that you build, you also have places where there's data that's kept in memory, so you can reuse the knowledge that you've inferred. And that can be alpha memory, which works off kind of the solution nodes, or the selection nodes, or you can have beta memory, which works off your joins. And so this is the Reedy algorithm. This is a way to just apply graphs in a way that makes it very efficient to do knowledge evaluation. And this is something that we use at my current employer right now, which is Cerner. And we use it to represent healthcare information. So we care a lot about if somebody has hypertension and it's moderate, that we really need to have a physician or a nurse recommend to them that they need to start thinking about rethinking their diet. But also, in some cases, maybe that blood pressure is so bad and based on their age that we really need to make sure that they're taking blood pressure medications. And so we have terabytes of data that we need to evaluate against all these complicated medical rules. And so we needed some sort of structure in order to store all that data and execute that efficiently. And so we leveraged Reedy behind the scenes to make that graph of that information. Now, earlier, I had talked about the fact that, as engineers, sometimes our jobs is to find ways not to write code. And so from this standpoint, there shouldn't be a reason to go out and write your own rules engine. There's lots of existing systems out there. There's Jess, there's Drools. More recently, there's Clara. And so you can leverage these instead, and these will implement the ready behind the scenes. But I'm going to say that I lied a little bit in saying that we leveraged an existing system, or that we should have. Maybe I was right in saying we should have. Because in reality, we actually built Clara. We decided that we wanted to take the ready algorithm and we wanted to leverage closure so that we could represent the rules in a way that was understandable to programmers but still explorable to non-programmers if we did it right. And so we thought, closure was the best syntax for that, and so out of that we built Clara. And by we, I actually say this guy did, Ryan Brush, who is a distinguished engineer at the company I work for. He built Clara, and the team I work with uses it heavily. But this leads me to the whole point of why I started this talk, which is Ryan Brush and I actually carpool to work together a lot. We both work for the same company right now. This is not our car. I wish it was. I actually love Pacers. They're amazing. But we carpool a lot, and since we both work in the same space, we both work in processing large amounts of healthcare data and being able to make decisions and choices based on the information in that data. We often talk about work a lot on the way to work. And we get into weird conversations. And one of the weird conversations we got into once was the purpose of a code review. It was like this big debate in our 20-minute commute. And the reason it came up is because someone was wrong on the internet, and they said that the purpose of a code review was to find bugs, which we laughed at that. I said, of course not. You do testing to find bugs. And we said, well, then how do you convince people that what the real purpose of a code review is? And we talked about how it's really about making sure we have the right patterns, and that we're using the right approach, that the code is understandable by humans, not just computers. And that led me to tell a story about one time when I was working early in my career, I got the fun of reviewing someone's code where they had to balance these 3 different variables around medications. So they needed to understand, does it work, which is that efficacy. They need to understand what is the cost, is the patient actually going to be able to afford this drug? And they need to understand the convenience. Nobody wants to take 16 large horse pills in the morning, nor do they want to have a shot every 15 minutes. So there's a convenience factor to getting patients to take their meds. And so you have to balance all 3. You can't just only favor one variable and say, here's your cheapest med, but guess what? You get to take it every 5 minutes. And the person who wrote the code to do that did something like this, where they implemented this Java sorting function, and it really favored that efficacy. We're going to get you drugs that really work. And I remember reviewing the code and telling them, I don't think this is the right approach. But I really couldn't put my finger on what they should do. I just knew that this wasn't the right way. I knew it wouldn't work. And so we talked through some other options, and they came back and proposed this, where it was like, okay, well, we'll just keep resorting the data over and over again on different variables, and we'll just keep picking the top 10, every time we resort it, and then we'll kind of intersect the results and find the best one this way. And that doesn't work either. Also, it's really, really ugly. And I think ugly is a good measure of bad code. And so what I realized later is after I had gotten more experience working with spatial reasoning and navigation systems throughout my career, that the real approach would have been something more like what I described earlier. Finding an approach that actually mapped to a multidimensional algorithm or data structure, like a quad tree, or that Z order, and that's really what they should have done. And then the code wouldn't have looked like this, of all these nested for loops accomplishing, random goals and not being able to understand it. And so this is the genesis of this talk, was that conversation, carpooling to work, and about how, when you see code like this, when you see really, really nasty code, that it's a sign that we haven't learned the right algorithm. That there's tons out there. There's a wealth of algorithms that we never were exposed to in undergrad. And so maybe it's time to pull open an algorithms book and crack it open again and start reviewing it. Whether it's the art of computer programming or what I call the Bible of algorithms, there's a wealth of knowledge out there. And if the concern is maybe those algorithms are too stale or the information is too outdated, well, that's the awesome thing about Wikipedia now, is you can do a depth-first search of it and just discover all of these things that you hadn't learned before that are really valuable to your work and apply them. Because I think at the end of the day, there's been so much research into algorithms and data structures that, whatever we need to do, there is a solution out there that fits it. And to be honest, it was probably from the 60s or 70s, because that was kind of the golden age of algorithm development. So with that, I'm Michelle Brush. I'm also a product of the 70s. And I'm the engineering director at Cerner Corporation for our population health space. I'm also the chapter leader of Girl Development and a co-organizer of Midwest I/O. And like I said, you can come find me later and I'll tell you all about all sorts of different heuristics you can use with A-star, or you can tweet at me or follow me on Twitter. So thank you very much.
So we have time for a couple questions.
All right.
Yeah, just raise your hand and somebody will come and get you. Thanks for waiting.
If it takes too much or you don't know, feel free to skip me. But about the Z tree, is there a quick way to describe how you might optimize, like, let's say, a point close to origin in quadrant 1? That's kitty corner to a like a point close to the origin in quadrant 4, something like that. How you would account for that or optimize since they're so far away in the.
Yes, yeah, actually use Hilbert curve instead, invented by David Hilbert, but that's from the 1800s, so I didn't cover that one.
One more. We've got someone in the back corner here.
You talked about graphs, and I was wondering to get your thoughts on, what are your thoughts on like Neo4j and their Cypher, which is also their sort of pattern matching and data extraction algorithm?
So I will admit that I've only done sort of the brief, hobbyist exploration of Neo4j. When I did a lot of my graph work, we were doing an embedded system, so everything had to be ANSI C and assembly, which was awesome. But so I've only really played with it, and so all I can really comment on is I think their interface is really fun to use.
Well, let's give another round of applause for Michelle Bush.
Thank you,
Michelle. That's some cool stuff.